Hello everybody, my name is Aji Gautama Putrada and welcome to my presentation. The title is ImbGAFS, the GA feature selection for AUC in bird strike prediction. Airplane bird strike is a term to describe an airplane colliding with a bird or a group of birds which can cause disruption to the aircraft and threaten the bird's safety. There have been many studies that have also tried to predict airplane failure using machine learning, some of which use MLP, SVM, linear regression, and random forests. Some problems that are still opportunities in the subject among else are imbalance problems and optimization. So our research aim is to create an airplane failure prediction using a machine learning method optimized using genetic algorithm or GA feature selection. The GA here is to optimize the AUC or for AUC maximization. The four machine learning methods are compared. Earlier we mentioned they are MLP, SVM, linear regression, and random forest. And for the imbalance, we use smooth for uh, and G-main selection. And lastly, we use GA with feature selection or our novel method called ImbGAFS. So this is our methodology. First, we obtain the airplane failure by birdstick dataset from Kaggle, and then we do dataset pre-processing. We use label encoders and other methods, and then we do prediction training using the four machine learning methods mentioned earlier. After that, we do ROC threshold selection with G-mean, and then the next step is to use GA to do AUC maximization, and lastly, we evaluate and we report our findings. So this is our optimal threshold selection algorithm. First, we collect several thresholds, sensitivities, and specificities from the ROC process using the soft labels and the actual labels. For each sensitivity and for each specificity, we calculate the G-mean using the following formula. And then lastly, we choose the most optimum threshold by using the argmax of the collection of G-means that we have collected in the process earlier. So this is the algorithm of our novel ImbGAFS objective function. First, we generate a random number. The random number has a range from 0 to 2 to the power of the number of features. This number is then converted into a binary number, and the binary number is converted into an array of Boolean values. This array of Boolean values is used to filter the original features into the new features called the subfeature. Then we train our machine learning model, our optimal machine learning model using the subfeatures, and then we optimize again the G-mean until we get the maximum value of our G-mean, and the G-mean value becomes the optimum value that is the output of our objective function, and that is the GA process. And this is the result of our first test, which is the implementation of smooth and the machine learning models. So we cannot measure the machine learning models with accuracy because it does not describe the performance of a model when it is going through imbalance problem. Here we use ROC to compare the performance. In the left side is the models without smooth, and on the right side is the models with smooth. Here we can see that smooth increases the performance of logistic regression, SVM, and random forest. However, it does not increase the capabilities of MLP. Also, we can see that in both scenarios, we can see that random forest has the most optimum results, and the most optimum result of all of them is the random forest with smooth. So for the next step, we use random forest with smooth for our optimum model. Now we test the performance of the G-mean threshold selection. As we mentioned earlier, accuracy can be used to measure the performance of our random forest model. So here we use sensitivity and specificity. Sensitivity measures the performance of the majority label, and specificity measures the performance of the minority label. Here we can see before the threshold selection, there is a very high imbalance between the majority label performance and the minority label performance. The G-mean is the aggregation of both the sensitivity and specificity. In the first result, the G-mean is 0.5. After the threshold selection, we can see that the measurements are more balanced. Here we can see, although there is a decrease in sensitivity, the specificity increases around 4 times. The result is the G-mean, again, the aggregation of the both values increase from 0.5 to 0.8. This shows the success of the G-mean threshold selection process. Observing the objective function landscape is important to see how complex our problem is in the genetic algorithm in our ImbGAFS method. Here we can see a part of the objective function landscape. Here you can see that there are many values in this part of the objective function. The many values in the graph shows that there is a chance of getting trapped in local optimum. To avoid getting trapped in the local optimum, we need to increase exploration and decrease exploitation. In genetic algorithm, that can be done by increasing the probability of mutation and decreasing the probability of the parent genetics. So here we can see this is the result of the feature selection of our novel ImbGAFS. These are the feature names in the dataset of the aircraft bird strike dataset. And here are the Pearson correlation scores of each feature towards label. And at the right side is the selection result of the ImbGAFS. Here we can see that the selection done by ImbGAFS does not take consideration the magnitude of the Pearson correlation. If it uses a threshold method, it will cut the features at a certain point. And this is a good choice. Why? Because by doing so with that stochastic type of method, here you can see that the result of the ImbGAFS feature selection increases the performance of the AUC and also the sensitivity, the specificity, and lastly the G-mean. All of them increase from the result of the machine learning prediction from the previous random forest method. And here we discuss the results and point out our research contribution. So first, airplane failure detection by birdstrike have been previously done by previous research, but none of them take into consideration the imbalance problem in the dataset. Here we use some methods to find a solution for the imbalance dataset. Secondly, previous methods have used G-mean threshold selection, and some previous methods has used AUC maximization. Here we use both of them to optimize the results of our machine learning model to get the best G-mean value. And lastly, we propose ImbGAFS, which is a novel GA feature selection. This method uses G-mean threshold selection as its objective function. Previous methods have used GA feature selection, but none of them have used G-mean threshold selection. And we prove that the use of ImbGAFS can improve the performance of failure detection by birdstrike. So this is our conclusion. First, we succeeded in implementing ImbGAFS, a novel feature selection method with G-mean selection objective function for datasets with imbalance problems. Then the imbalance problem in our research is moderate, where 6% of the dataset belongs to the minority label. Random forest is more optimum than MLP, SVM, and linear regression on airplane failure detection by bird strike. And lastly, ImbGAFS improves the random forest G-mean value from 0.80 to 0.82. And that is the end of our presentation. Thank you for your attention. If you have any questions, let's do a discussion in the next session.